Hey everyone, and welcome back to CodeAccessHub, the place where we get into the nitty-gritty of fundamental AI concepts. So this is part 2 of our big series on Ilya Sutskever's top AI papers. And today, we're tackling a really cool question. Why do things seem to get more interesting before they get, well, boring? We're going to dive deep into a paper called Quantifying the Rise and Fall of Complexity in Closed Systems. And you know what? The whole idea behind it is inspired by something most of us do every single morning.
Yeah, it all kicks off with something super familiar, pouring cream into your coffee. I mean, think about it. First, you've got these two really simple, separate layers, right? The black coffee, the white cream. Then for a moment, you get these beautiful, complex swirls and patterns. It looks amazing. But then, it all just fades away into a simple, uniform, kind of boring brown liquid. That little journey, that interesting roller coaster of complexity, that's the mystery we're going to unravel today.
Okay, so here's where it gets really fascinating. That simple thing we see in our coffee cup, it actually seems to completely contradict a fundamental law of physics.
So on the one hand, you've got the second law of thermodynamics. This law says that entropy, which is basically a measure of disorder, can only go up in a closed system. Things are always supposed to get more mixed up, more chaotic. But on the other hand, our eyes are telling us something different. We literally see complexity rise, peak with those incredible swirls, and then crash back down into a simple mixture. So what gives? How can both of these things be happening at the same time?
Well, to solve this little paradox, we have to get a bit more precise. We need a way to actually measure this interestingness that we're seeing. And the paper gives us a tool for that. It's a formal idea they call apparent complexity. A really good starting point for this is an idea called Kolmogorov complexity. And the concept is actually pretty straightforward. Basically, the complexity of something is just the length of the shortest possible computer program you'd need to describe it perfectly. So think about a simple pattern, like a string of a million A's. That is super low complexity, right? Because you could just write a tiny program that says, print the letter A 1 million times.
But there's a catch, and it's a big one. Imagine a screen full of random TV static. According to Kolmogorov complexity, that static has the highest possible complexity. Why? Well, because there's no shortcut. The only way to describe it is to literally list out the color of every single pixel. But let's be real, when you look at that static, does it feel complex or interesting? No way. It just looks like random noise. This is where the paper gets really clever. It proposes a brilliant tweak. Instead of trying to measure the complexity of every single tiny particle, that raw microscopic state, let's measure what an observer, a person, actually sees. And they call this apparent complexity. It's basically the complexity of a smoothed out, or as they call it, a coarse-grained version of what's going on. This image here illustrates the idea perfectly. Look at the left. That's the messy, pixel-level reality. It's got super high raw complexity, just like that TV static. But now look at the right. That's the smoothed-out version. That's what our eyes actually pick up on, a simple, elegant pattern. So this process, this coarse graining, is all about ignoring the random noise so we can see the real structure underneath. All right, so now we have our tool, apparent complexity. The paper is ready to put it to the test. And they do this in a kind of digital laboratory, a simple simulation called a cellular automaton that's designed to act just like our coffee cup. So the researchers run this really important experiment, basically an A/B test with two different models. In the first one, the non-interacting model, the little coffee and cream particles just wander around randomly. They don't bump into each other or anything. But in the second one, the interacting model, they can actually collide and swap places, just like real molecules in a liquid would.
And let me tell you, the results from these two simulations are like night and day, and they hold the key to this whole mystery. Let's take a look at the data.
Okay, first up, the non-interacting model. See that blue line? That's entropy. It goes up steadily, exactly like physics says it should. No surprises there. But now look at the green line. That's our interestingness, our complexity. It's totally flat and low. It's just boring. When the particles don't interact, nothing interesting ever happens. No cool patterns form.
But now, look at the interacting model. This is the money shot. See? While entropy, that blue line, is still climbing steadily toward maximum disorder, look what the green line for complexity does. It shoots way up, hits a peak, and then slowly falls back down. This graph, this is it. It perfectly captures that interesting roller coaster we see with our own eyes in the coffee cup.
So it turns out interaction is the secret ingredient. It's the ability for particles to actually push each other around that allows those big, intricate structures, the swirls and the tendrils, to even form at all. Without interaction, you just get a blurry, boring, featureless mess. Okay, so this brings us to the final piece of the puzzle. We figured out why complexity rises, but why does it fall? Why does everything become simple again at the end?
Well, the paper gives us a really elegant answer, and it brings us right back to where we started. The final state is simple because it's just so easy to describe.
And that is the solution to the whole paradox. This state of maximum disorder, maximum entropy, that perfectly mixed, uniform liquid, is actually also a state of maximum simplicity. It takes almost no information to describe it. You just say it's a uniform mixture. All that detailed, complex information that was in the swirls, it's been all smeared out into random noise. And that's exactly what our coarse graining process is designed to ignore.
Now, apparent complexity is just one way to think about this. The paper actually connects this idea to other really cool concepts that also try to get at what meaningful complexity is. For instance, there's something called logical depth, which thinks about the time or effort it takes to create something. Those coffee swirls don't just pop into existence, right? They take time to develop. It's just another way of looking at the same fundamental pattern.
And there you have it. That's how the Coffee Automaton gives us a real, measurable model for the rise and fall of interestingness. A pattern that, once you see it, you start to see everywhere.
So if you enjoyed this little deep dive, please make sure you subscribe to the CodeAccessHub channel. We're going to be breaking down all 30 of Sutskever's top papers, plus a ton of other foundational AI concepts.
But let's think bigger for a second, because this isn't just about a cup of coffee. Our entire universe started in a very simple, low-entropy state, and physicists think it's heading towards a very simple, high-entropy heat death in the distant future, which leaves us with a pretty mind-blowing final thought. Is it possible that we, right now, and all the incredible complexity of life, that we're just living in the middle of the universe's own interesting roller coaster? Something to think about for sure. Let us know what you think down in the comments.